Hello dear students, welcome back to another video lesson. In this video lesson, we are going to analyze the chapter Magnetic Effect of Current. Theoretically, you might be fit on this chapter, I know. Now, how these all theories came in the exams. Last 2 years, past papers from different regions of CBSE, we are going to analyze in this video lesson. Okay, let's go here. The chapter Magnetic Effect of Current. Here, mainly theory questions are there. Rules are there, like right hand thumb rule, Fleming's left hand rule, then Maxwell's screw rule or Cork's rule. Both are same, right hand thumb rule and Maxwell's rule. So rule statement is very important. How to apply it in the questions? We can see few questions there. Then diagram based or device based questions are there. These are the major area of this chapter. Devices like solenoid. Then this domestic circuit is there. Force on a conductor concept is there. Like that, device and diagram based questions also you can expect. Mainly 6 marks question is to come from this chapter. Average every year that questions are there. 6 mark questions. Some years it gone up, otherwise it will be 6 marks. So be ready to score this 100% of these marks, like 6 out of 6 from this chapter. Let's go. The first question. In domestic electric circuit, this question is regarding domestic electric circuit. The wiring with 15 ampere current rating is for the electric devices which have, see 2023, the set 1 from the 31. Domestic circuit we studied. In domestic circuit we have different ratings of the appliances we have. Basic from bulbs, electric fans and all the basic devices. Then we have iron box we have, electric kettle we have, electric heaters we have, electric geysers we have. Then high-end air cooler or air conditioners, ACs we have. AC also different powers, AC we have available. So these all devices you studied, they are connected in parallel between live and neutral wires. So parallel circuit connections are used in domestic circuit, all of you know it. But they need different ratings of current we have. So mainly in our domestic circuit, we have 5 ampere circuit, 10 ampere circuit, 15 or 32 ampere circuit we have. All the basics have 5 ampere circuits they do, electric bulb, fan, etc. and all. Here the question is 15 ampere current rating is used for which one? Of course, those devices having, appliances having very high power, they are connected to 15 ampere circuits. So options, let's see. Higher power rating such as geyser, lower power rating such as a fan, metallic bodies and low power rating, non-metallic bodies and high power rating. So here we have higher power rating only, of course. Metallic body and non-metallic body, the difference is only with earth wire only. So metallic bodies have earth wire also connected. You know earth wire is a safety measures. We'll be coming to that question later. So here the option is simple. Higher power ratings we have to use it for 15 ampere. If it is like electric fan, low power, then 5 ampere current is fine. All of them works on same voltage. You know how much it is? 220 to 240 volts we have using. Because they are in parallel circuit. In parallel circuit, all the devices are connected to same potential difference or voltage. How I got it? Let's go for the next question. The resultant magnetic field at point P situated midway between 2 parallel wires placed horizontally, each carrying a steady current I is. See, typically logic question it is. So we have, is regarding magnetic field. We studied that whenever electric current is passing through a conducting wire, around the conducting wire we get magnetic field. And the direction of magnetic field is get by right hand thumb rule. If thumb shows the direction of current, then the curled fingers or the winding fingers gives the direction of magnetic field. So here in this question, we have 2 straight conductors, parallel conductors. They are kept horizontally. Current I is passing in the same direction. So they are parallel conductors. Then if you consider a point midway between this one, exact midway point, what will be the net magnetic field? That is the question. So you have to use the direction of magnetic field first of all. Then midway between and same current is there. So the magnitude of the magnetic field will be same. You have to check the direction only. Whether they will be added up or they have to subtract, that we have to check it. Okay. So, to the resultant magnetic field at point P, here is the point P. Situated midway between two parallel wires, each carrying a steady current I is. Option C, in the same direction as the current in the wires. In the vertically upward direction. 0 in the vertically downward direction. These are the options. So let's see. Of this, suppose I am giving name A and B. Current I is passing through A towards our left side. So if you keep it, the thumb along this way. Then curled fingers shows that the below the wire, it is into the board, and above the wire, it is out of the board. So at P, due to A, the magnetic field is into the board. Yes or no? So this is into the board. The magnetic field lines we represent cross into the board and dot out of the board. Got it? Now, due to B, the wire B, if you keep it, the point P is above the wire. So it is right hand thumb is in this direction. So curled fingers if you keep it below the wire into the board and above the wire is out of the board. So due to B, the magnetic field here it is out of it. So you can see here the magnetic field due to A is into the board. Same current is passing through B also, and due to B, the magnetic field is out of the board. So equal and opposite magnetic field is there in the same point. If add up, they'll get cancel each other. So 0 will be the resultant magnetic field. Option C is correct answer. You might got the answer. Let's go for the next question. An electric iron of 1500 watts, 200 volts and a flashlight of 500 watts and 200 volts are used in homes. The rating of fuse to be used should be. So regarding it is fuse. You know, in domestic circuit, electric fuse is another safety device. We have two safety measures, earth wire and electric fuse. Electric fuse protect the devices from overloading or high current passing through it than their rating. So a fuse have particular value of the rating which have a level of the current which is allowed to pass through the device. If extra current comes, the fuse melt or break down, then device will be safe. So let's see, so we have to calculate the current passing through the device. That's all. So here first one, iron. For electric iron, we have power is equal to 1500 watts and voltage is 200 volts. Is it? Then here we have P is equal to V into I gives you I is equal to P by V. That is 1500 divided by 200. That is, if you divide it, 0 zeros cancels. 15 by 2 is 7.5 ampere. So current through the electric iron is 7.5 ampere. It's required current. Now let's see for the flashlight. Flashlight power is equal to 500 watts and V is equal to 200 watts. Then I is equal to P by V. So we get 500 divided by 200, that is 2.5 volts. So current is 2.5 volts to be in flashlight. And in electric iron, it is 7.5 ampere. So here the current is 2.5 ampere. You know, when we detect the fuse, suitable fuse should be just above the allowed current. So here the question is, the rating of the fuse to be used should be. So here 5 ampere is there, 10 ampere is there, 15 ampere, 20 ampere is given. So the combination actually is there. For flashlight is 2.5 ampere is the current allowed. I mean the rating is there. So just above 2.5 ampere, this is 5 ampere. So the option, some mistake is there. For 5 ampere can be maximum to flash lamp. Then for electric iron, it is 7.5 ampere. So just above 7.5, 10 ampere can be. So two different options are there, like for flashlight A and for electric iron B it is there. Same fuse, if you connect for both, it won't work, because if 10 ampere current pass through flashlight, it will damage. Maximum it can be just above only. So available is 5 ampere means you can use it. 4 ampere maximum it can be. Hope you got it. Let's go for the next question. A positron enters a uniform magnetic field at right angles to its as shown. So here the figure is given. In this one, a positron is entering. The direction of force experienced by the positron will be, so force on a moving particle. We have a moving charge creates a current. Around the current we have a magnetic field. If this charge is moving in an external magnetic field, there are two magnetic fields, one externally applied and the magnetic field produced by movement of this charge. So interaction of two magnetic field comes there and the charge experience a force. If a conductor is kept, then conductor also experience a force. What is the direction of force? We have Fleming's left hand rule. If index finger shows the direction of magnetic field and middle finger shows the direction of current, then thumb gives the direction of force or the motion of the particle. If so, here is given, positron is a charge which enters the magnetic field. You know, in normal grade 10, the questions used to be 4 types of charge you can get it. 4 examples of charges, like 2 types we have positive charge and negative charge. Electron is a negative charge. Electron we have negative. Then proton, alpha particle. Then positron. These all are, so positron, alpha particle, then proton. These all are positive charges. Why I mentioned this one means, in our grade 10, these are mainly the common charges which gives in the questions. The positive charges, in which direction they are moving, that will be the same direction of current. While using Fleming's left hand rule, you have to use middle finger as the direction of current. So the direction of positive charge will be the direction of current. Then if negative charge is given, then opposite should be the middle finger kept, because the direction of current is opposite to the direction of negative charged particle. You know, our conventional current direction is along the direction of positive or opposite to the direction of electron. Hope got it. So here, in this case, see, magnetic field is towards left. Then positron is going upwards. Then to which direction with respect to the paper or this board, what direction will be the direction of force? So it will be deflected in that direction. So for that purpose, we have to use the Fleming's left hand rule. So fix one finger first, magnetic field, index finger to that direction, kept. Then positron is moving upward, so current also upward, middle finger upward direction. Then stretch your thumb, so you can see this thumb is moving into the board, or with respect to your question paper, if you check, it is into the page. So option is C is the correct answer here, into the page. Once more, fix the first finger. Don't keep all the 3 fingers together at the time. First finger first, magnetic field in that direction zone as per the figure. Then positron is moving in this direction, upward. So middle finger in upward direction. As per the board I am keeping. Then stretch your thumb. Thumb is into the board. So answer is into the page or into the board. So option is C is the correct answer. Hope you got it. Concept: force on a current carrying conductor or force on a charged particle moving in a magnetic field. You got it. Let's go for the next question. The correct pattern of magnetic field lines of the field produced by a current carrying circular loop is. So there is a circular loop. So in that, if you pass current, it will have a magnetic field direction. You know, right hand thumb rule we can use to find the direction of magnetic field due to a straight conductor as well as a circular conductor. So if you know the direction of current, then direction of magnetic field can be produced. So this figure you are familiar in your textbook also. NCERT textbook, these figures are given. So here see. Then A straight conductor, if you bend and form a circular loop, then you know the benefit. The magnetic field lines in the interior region of the loop will be in same direction, hence it will be stronger magnetic field. So here see that A, you check it. Upward it is this out of, below it is outward. Two different directions given. That's wrong. A is not the answer. B, you check it. Magnetic field is from that to this one. Here this opposite. This also wrong. C, you check it. Magnetic field is okay. All the magnetic fields are from right to left is going. So this way the coil is kept. If you keep it this way, magnetic field is getting in. Same direction and at the center is same this way. Then here see circular loop is there. So option C is correct answer here. The same figure is there in your textbook, NCERT textbook. And see D. D actually only here is the magnetic field showing and that's wrong. Hope you got it. This figure you have to practice also. Sometimes they will ask to draw this figure, pattern of the magnetic field lines produced by a circular current carrying loop. Keep in mind this figure. Next question, let's see. An alpha particle. So here see alpha particle came. Alpha particle has a positive charged particle. You got it. What's the specialty? Positive charged particle is moving, then that is the direction of current. Enters a uniform magnetic field as shown. The direction of the force experienced by the alpha particle is direction of force. Fleming's left hand rule, you have to use it. Left hand rule. So alpha particle, see alpha particle is moving downward and magnetic field is that direction. So first index finger to the direction of this towards left. Magnetic field is there. Alpha particle downward it is. So middle finger downward, thumb out. See stretch. Magnetic field, current, then thumb is out of this page. Check the options. Towards right, towards left, into the page, out of the page. Answer is out of the page. D is the correct answer. See 2023, another question. So MCQs questions are there in this chapter, 1 mark, one of the probable questions regarding force. Fleming's left hand rule it is. Let's take the next question. See again another set. We have 2023, 31 another region. So different region questions I collected together. So it will be easy for you which all levels questions can be there. An alpha particle again enters a uniform magnetic field as shown. The direction of motion of the alpha particle is, here see, magnetic field is along this direction, towards right it is. Then alpha particle is upward. So here see, the index finger in this direction, towards right. Then current is upward, so keep it upward, middle finger upward. Then see thumb out of the page again. It is out of the page. So answer is again out of the page. Here see, both direction of alpha particle and magnetic field is changed than the previous one. See, previous one it was alpha particle downward, magnetic field right. Left it is. Then here it is opposite. Both are changed, hence answer is same, will be out of the page. Let's take the next question. A constant current flows in a horizontal wire in the plane of the paper from east to west as shown. Here see, east to west the current is passing through. This is the east-west direction. The direction of the magnetic field will be north to south at a point. So at a point here, the magnetic field will be north to south. Which is that point? That's the question. A current is passing through the conductor. So direction of magnetic field is given by right hand thumb rule. You have to use the right hand thumb rule. So that magnetic field is from north to south in which direction? So here see, east to west the current is passing through. So if you keep it east to west, thumb is towards west, right hand you have to use it. Then see the curled fingers is moving. At a point here it's moving into the page, then it's coming down, then coming towards you, out of the screen, then coming upward. See, this is the circle. Is it? So if you divide into 4 points, a point top is moving away from you or towards the screen is coming. At a point here, it's moving top to bottom. So top to bottom means top is the north, bottom is south. North, south. So north, south is coming at a point behind or below this wire it will be, as per the question if you check. So see the option, directly above the wire, directly below the wire, located in the plane of the paper on the north of the side, located in the plane of the paper on south side of the wire. So correct answer is directly below the wire. So the wire is kept on the paper. So as per the paper, you have to check it. If you keep it, the fingers is moving top to bottom in below point. The behind point is coming down. Above point here is it. That is from south to north. Upward is going. Is it? This way is coming up. Hope you got it. So right hand thumb rule, you have to use it. Let's see the next question. The pattern of the manned field produced inside a current carrying solenoid is, solenoid is one of the important devices, you know. A straight conductor, manned field is there in outside, right hand thumb rule you can use it. That conductor, if we bend to a circular loop, we found that its magnetic field become more stronger in the inside, interior part of the loop, because the magnetic field due to each part of the loop will be into the same direction. So one turn is there, then constant magnetic field is there inside, and it becomes stronger. Now, if it is made to a coil, many turns you make it, we call it as solenoid. Each turn will produce same magnetic field in same direction. So it will be add up and we get a uniform magnetic field inside the solenoid. So a stronger magnetic field we get inside the solenoid. And the benefit is, as much you need the magnetic field, you can increase the strength by increasing the current. So solenoid is an important device. It's also called electromagnetic if an iron, soft iron core is kept inside the coil. It can be used to magnetize a material. So here, the pattern of this inside the current carrying solenoid it is. Option A, so you have inside the solenoid, it will be parallel lines because it is uniform magnetic field lines. So A is the correct answer. Quick. B, it is just because of a straight conductor only. So if a straight current carrying conductor is there, then it will be like, see, this way is coming out. Outward is coming out. So the current is passing downward here in a straight conductor. Here, this is the south here, suppose north is there, then outside is wrong only. So this cannot be anywhere. D, see it's going, it's due to a single loop, current loop only. So A is the correct answer for the solenoid. Let's check and solenoid act as a bar magnet also. You know, bar magnet of north pole, south pole, and magnetic field at the end of this bar magnet will be more stronger. Outside start from north to south, inside south to north is there. So solenoid and bar magnet have same type of magnetic field. There's a question is there, we'll come to in that question later. Next question, let's check. Strength of magnetic field produced by a current carrying solenoid does not depend upon. So strength of the magnetic field by a solenoid depends upon, you know, the number of turns, you know, intensity of current, you know, number of turns per unit length also. Then the material what is kept inside the interior part of the solenoid is also a factor there. If you use a strong magnet, if you want to make it, you can keep a soft iron inside it, act as a strong magnet, than without iron. So like that different terms are there. So does not depend is the question. Number of turns in the solenoid, of course, is a factor on which it depends. B, direction of the current flowing through it. Direction of current is not a factor to depend, but intensity of current is a factor. So direction of current is not depending. So B can be the answer. Wait to confirm. C, radius of solenoid, of course, will be a factor because bigger radius means area will be less. So, area will be more. So this length of the solenoid will be less, we can say. So radius is a factor. Then material of the core of the solenoid is also a fact. So direction is the concept here. Direction of current flowing through it do not depend upon intensity of magnetic field, but direction of magnetic field, it depends. Let's go to the next question. A rectangular loop ABCD carrying a current I is situated near a straight conductor XY such that the conductor is parallel to the side AB of the loop and is in the plane of the loop. So here we have a loop ABCD have the loop and their current is passing here this way and this way the current is passing. Near to that one side AB you keep another conductor of XY. Current I is passing through it in upward direction. So if it is kept in current is passing through AB, it will produce a magnetic field. In that magnetic field, we are keeping an XY as an independent straight conductor. So of course, XY will experience a force. Because XY also create a magnetic field. So interaction of two magnetic field comes there will be a force on XY. Direction of that force, we can use Fleming's left hand rule, so it'll be fine. So here, if a steady current I is established in the conductor as shown, the conductor XY will, what happened to this XY? Just use the Fleming's left hand rule. So AB, current is moving upward. Because of that, magnetic field in the left side will be, if you use the thumb upward, then left side the magnetic field is out of the board. So here the magnetic field is out. A dot I am putting, out of the board it is. So magnetic field is out. Index finger or forefinger finger out of the page you have to keep it. Then on XY current is upward, so middle finger upward. Then where is the thumb goes? Thumb go to that direction. That direction means there is AB. So this conductor have a force which will make them to move towards AB. So XY. So once more, by using right hand thumb rule, due to AB, what is the direction of magnetic field where XY is kept? There the magnetic field will be out of the board because it is on the left side. So it is moving out. So forefinger or index finger there. In XY place, index finger, the magnetic field is out of the board. Current is upward, so middle finger upward you keep it. Then stretch the thumb moves towards the right. So here the conductor XY will have a force which move towards AB. See the option? Yeah. Move towards the side AB of the loop. That is the correct answer. Now, there may be a doubt comes. See, XY also will produce a magnetic field there. In that magnetic field, we are keeping this loop complete. Is it? As a square loop, their current is moving to which different axes, different arms, sides will be in different direction it is. AB it is upward, BC it is that way, CD it is downward. So in the same loop, at AB there will be a force, CD also one force will be there. It will be cancelled out. So XY is acting there, XY will be moved towards AB. Hope you got it. Once you feel doubts, you pause the video and watch it again, then confirm it. Let's go for the next question. The current carrying device which produces a magnetic field similar to that of a bar magnet is very easy question. Is it? Similar to bar magnet, which device gives you the magnetic field? Current carrying should be. That's nothing but our solenoid. So option C is the correct answer. Check other options. What is the difference there? One, straight conductor. A straight conductor is there. Then around this the magnetic field are in concentric circles. Concentric circles there. There is no like north to south like that. Concentric circles are there. That's not like of bar magnet. B, a circular loop, a single loop is there. This cannot be. D, a circular coil is given, just a coil. One upon one if you did, then it won't have a magnet. So cylindrical coil, it will be giving a solenoid and that will give as a bar magnet. Let's check the next question. An electric kettle consumes 1 kilowatts of electric power when operated at 220 volts. The minimum rating of the fuse wire to be used for it is, so electric kettle it is, okay, it uses 1 kilowatt of power at 220 volts suppose. What is the fuse rating of this kettle we have to find? So actually this combination of two questions, two chapters we can say. From electric current density chapter, by using the power equation you can find how much current it requires. We have power P is equal to V into I or I is equal to P by V. So it gives power is how much? 1 kilowatt, that is 1000 watts divided by V, the voltage is 220 volts. 220 volts. So it's approximately equal to 4.5 ampere. That is I. So this is the current rating of this kettle. It's not 4.5 ampere current only. So check, the fuse should be just above 4.5. So it is 1, 2, 4, 5. Answer is 5 ampere is the correct answer. If you use 4 ampere here, what happens? It always will break. Because kettle to work, it needs 4.5 ampere. If you use a fuse rating below this allowed current, it won't work. Hope you got it. Let's see the next question. The magnetic field inside a long straight current carrying solenoid is 0, decreases as we move towards its end, increases as we move towards the end, is same at all points. Very simple question. In solenoid we know, inside the solenoid it is uniform everywhere. So it's same every point. So D is the correct answer. Next question. An electron projected towards east is deflected towards south by a uniform magnetic field. The direction of magnetic field is, so direction of magnetic field you have to find out. Here electron is projected moving, hence it get a deflection, means a force extra is getting. So movement of electron is there, force is there. In that combination, what is magnetic field? Some students may will confuse. Direction of magnetic field we use right hand thumb rule, you know. But here force is there and direction of electron is mentioned, that is current, hence we have to use Fleming's left hand rule. In that way, what is the direction of magnetic field you have to find out. So in this case, north, east, west and all given. On your paper, please draw the normal north, east, west direction. Don't think about in classroom what is north, west and east. Okay, don't need to ask your teacher that where is the north, where is south and all, no need to ask. Directly you can use normal what we write. This is north, then this is south. Here, this is east and this is west. So, in this question, an electron is projected towards east. So, electron was supposed to move towards east. Electron. It is deflected towards south. So, deflected towards south means it get a force, hence it moved downward. It's moved downward. So, force is towards south. As per this paper I am doing, as per the board I am doing it. Towards south is the force. Now, what is the direction of magnetic field is the question. So, if electron move towards east, current will be towards, yes, west it will be. Because in the previous slide I told you, electron moves in the opposite direction of current. So, electron moves east means current will be towards west. Then, force is downward here. So, thumb is down and this middle finger should be towards west. So, check. This way will be. Thumb is downward here and current should be, this current should towards west side. So current towards west and thumb towards down. Then check, this is the concept. Middle finger in this direction, west, thumb downward, south, then forefinger, index finger gives the direction that is into the page. Check the question. Here is the upward, downward, towards north, towards west. So here see, as per the page you check. This, it is into the page. Into the page means downward it is. If this way, outward. This way, inward. As a thumb downward because of south. Thumb is this direction, south direction. Middle finger towards west direction because electron is moving towards east. Then this index finger is into the page, that is downward. So B is the correct answer. Hope you got it? Fleming's left hand rule, use it. See, in a question, simply ask direction of magnetic field. Due to a straight conductor, you have to use right hand thumb rule only. If force is mentioned and magnetic field is mentioned, current is mentioned, then Fleming's left hand rule, you have to use it. Next question, let's check. A student has a long, straight, thick copper wire. A long, straight, thick copper wire. If he passes a current in this wire, he would get a magnetic field whose pattern must be. See, 2023, the question came and one of the region. So, in a long, thick copper wire is there. Around this, he will get a magnetic field in which pattern? Very simple. Radial lines originating from the wire, concentric circles centered around the wire, straight lines parallel to the wire, straight lines perpendicular to the wire. You know, right hand thumb rule, just thumb gives the direction of current, then curled fingers, so circular form, concentric circles around this conductor will be the magnetic field. So option B is correct answer. Concentric circles centered around the wire, that will be the question. So here, if you do, it will be like, if this is the direction of current in a conductor, then the concentric circles, if you make it this one. So if thumb is there, then this way, H will be there as a direction of magnetic field. Here is the next question, assertion and reasoning type. In this chapter, many questions like that there. Let's go through it. Assertion. the strength of the magnetic field produced at the center of a current carrying circular coil increases on increasing the number of turns in it. Yeah, sure, assertion is correct. So on a circular coil, what is the benefit? If you increase the number of turns, the magnetic field also increases. That's the main benefit of a electromagnet or solenoid or circular coil, because for a bar magnet or natural magnet, the magnetic field is fixed. You can't increase, you can't decrease. For that, you have to change the shape or the size of the magnet. Here, just on the same coil, you can increase the magnetic field either by increasing current or increase the number of turns or keep a soft iron core inside it. So, assertion is correct. Reason: the current in each circular turns has the same direction and the magnetic field due to each turn then just adds up. So, current is same direction and magnetic field also same direction. So, they will add up. So, total magnetic field increases. Exactly correct, and that is a correct explanation. So, option A is correct. 2023, one of the region question. Pause the video and analyze the question statement again. Let's go to the next question. Assertion: magnetic field lines do not intersect each other. Of course, we studied it. If two magnetic field lines intersect each other, then at that point, if you keep a magnetic compass which gives a direction, have to show two directions at a time, which is not possible. Magnetic needle is the compass. Magnetic compass is used to get the direction of a magnetic field at a point. So if two magnetic field lines intersect, then at that point, they have to show both directions. It's not possible. Hence, we know two magnetic field lines never intersect. Assertion is correct. Reason: magnetic field lines are imaginary lines, the tangent to which at any point gives the direction of the field at that point. Yes. So the tangent gives the direction at that point. Hence, these directions cannot meet at a point. So both are correct here. So two tangents, like if you draw it at a single point, it cannot meet each other. Hope you got it. Then here option, both are correct only. So in second case, it's not mentioned that at that point a compass have to show different direction at a single point. That's not possible. But B is correct only. So option B will be more accurate, I think. Both assertion and reason is correct. And reason is not the exact expression of the first case. First case, the reason you have to give. No. What is the reason? At that intersecting point, the magnetic compass have to show two directions at a time. This is not possible. But how the direction is given is mentioned B. B is correct only. Hope you got it. A current carrying straight conductor experiences a force when placed perpendicular to the direction of magnetic field. Of course, it's correct. Whenever a current carrying conductor is kept in a magnetic field, it gives a force for you, because there will be interaction of two magnetic field lines. One outside magnetic field and the conductor also produces a magnetic field. So together there will be an interaction. So there will be a force. Assertion is correct. Reason: the net charge on the current carrying conductor is always zero. So reason is not linked with the magnetic field only. But reason is correct. Net charge is zero on a conductor. Sure. Because conductors are made up of atoms. In an atom, equal number of negative and positive charges are there. So atom as a neutral, So though the free electrons are moving through the conductor, the total number of negative charges and total number of positive charge inside the atoms, inside the conductor will be same. So net charge on the conductor will be zero only. Neutral will be. Both are correct only, but not the correct explanation. So R is not the correct explanation of A. The next question. Two magnetic field lines around a current carrying straight conductor do not intersect each other. Of course, the same topic we done. So concentric circles they are. So never two lines intersect each other. The magnitude of the magnetic field produced at a given point increases as the current through the wire increases. Sure, as the current increases, magnetic field increases. But that is not the reason for the first case. Okay, so as the current is increased, more bigger and bigger cell you are getting. But for a same conductor, current is constant, So different circles are there. That depends upon the distance actually. As you move far from the conductor, the magnetic field will be weaker and the circles will be much apart. Okay, bigger radius will be there. Nearby it will be small radius, stronger magnetic field is there. So both are correct only, but not correct explanation. Assertion and reason are true. Reason is not the correct explanation of assertion. Both statements are correct. Let's take the next question. Magnetic field interact with moving charges and not with charges at rest. Yeah, exactly. Only moving charges create current. Around the current we get magnetic field. Is that fine? So varying electric field only we can say. Is it moving? Then only it produces magnetic field. If the charge is at rest, it do not produce any current. So there is no magnetic field. So assertion is correct. Reason. Charges produce magnetic field only when they move. Correct. Exact. So A is the correct answer. Both are correct explanation of assertion and reason. You got it. Next question. See another one more question. A uniform magnetic field exists in the plane of the paper as shown in the diagram. In this electric field, an electron and a positron enters as shown. The electron and positron experience forces. See here, the magnetic field is along this direction. We studied positron is positive charge, electron is negative charge. Then you know how to get the current direction. So here, electron is moving downward. So here, because of this, current I will be in upward direction. Then positron is moving upward only. So there also due to I will be upward direction only. So magnetic field along that direction. Current in upward direction, middle finger upward. Then thumb you move, that thumb is into the board or into the page. In both cases, current are in same direction. Why? Electron is moving down means current will be upward. Positron is already upward, so current is upward. So in both cases, current is same direction, same magnetic field. So force will be in same direction will be, and that is into the paper. Check the options. Both pointing into the plane of the paper. Yes, correct? Check all options. Which is more accurate, you have to get it. Both pointing out of the plane of the paper. No, B is not. C, for electron pointing into the plane and out of the plane for the positron. No, both are in same direction. Current is same direction. D, pointing out of the plane for the electron and positron into the plane. No. Option A is the most accurate. So A is the correct answer. Take utmost care. Electron moving down means current is not out in. Current is actually same direction, upward only. Opposite of electron is current. And for positive charges, current is the same direction. So positron upward only. Hope you got it. Next question, let's see. Assertion reason again. The deflection of a compass needle placed near a current carrying wire decreases when the magnitude of an electric current in the wire is increased. That is wrong, is it? If magnitude of the current is increased, it becomes more stronger magnetic field. Is it? So deflection have to be increased. So assertion is wrong. See, reason. Strength of the magnetic field at a point due to current carrying conductor increases on increasing the current conductor. So reason is correct, assertion is wrong. So assertion is false and reason is true. D is the correct option. Is the 2020-24. Here, current increases, then magnetic field also increases. So strength of the magnetic field at a point due to current carrying conductor increases on increasing the current. That's showing the opposite direction, is it? Because deflection of the compass near a current carrying wire decreases is showing. It will increase, of course. Next question, let's see. Magnetic field lines never intersect each other. Of course, that's correct. If they intersect, then at the point of intersection, the compass needle would point towards two directions, which is not possible. Yeah, exactly. See, previous one look like similar we done. Their reason was correct, but not the correct. Here, it is correct as well as explanation of the assertion. So, both assertion reason correct and they are correct explanation. So, A is the correct answer. Next question. The intensity of magnetic field produced at the center of a current carrying circular coil increases the number of turns on increasing the coil. Of course, strength increases on number of turns if you increase it. The intensity of magnetic field produced at the center of a current carrying circular coil increases on increasing the number of turns. So assertion is correct. Reason: the current that flows in each turn of the coil has the same magnitude and same direction, and the magnetic field due to each turn just adds up. Exactly correct. So A, both are correct, and as reason is correct explanation of assertion. Let's take the next question. Two magnetic field lines. So here now we comes to the MCQs parts came. Now 2 marks and 3 mark questions from this chapter we are going to discuss. My dears, whenever you feel doubts, you pause the video and clear cut it. Then check the answers, what are you getting correct. Okay, next question is, two magnetic field lines do not intersect each other. Why? Yeah, see, just before we got that assertion recent case. If you just slide it back, you'll get it. What is it? If two magnetic field lines are intersecting, then at that point, a magnetic compass have to show two directions simultaneously, which is not possible. Hence, it cannot be intersecting. You got it first. So, two intersection point, it's not possible. Because there, the magnetic compass have to show two direction, which is not possible. Now, second part, how is a uniform magnetic field in a given region represented? Draw a diagram in support of your answer. So, how to use a uniform magnetic field? See, one MCQ question was there this. Uniform magnetic field is given by parallel and equally spaced lines. So, equally spaced lines, if you use it, we will get the uniform magnetic field. So, for that purpose, we can use the lines like so some parallel lines, you just make it, and same direction should be marked. It shows you uniform magnetic field. So this is the answer for second part. Now why it is showing is equally spaced parallel lines, same direction. So uniform magnetic field will be there. If it is curve or space is different, then it will be varying magnetic field. Hope you got it? Is a 2024 question in one of the region. Let's take the next question. Draw the pattern of the magnetic field due to a straight current carrying conductor, indicating the direction of current in the conductor and the direction of the corresponding magnetic field lines. So, a simple 2 mark question it is. 2024 in one of the other region is the question came. So, straight conductor, you have to draw a straight conductor first of all. A straight conductor. So, here is the current passing I through this. In upward direction, current is passing. Then right hand thumb rule here is, so there we know the magnetic field lines are moving around it. So, you have to use concentric circles around it. So, for that, circles if you draw, same radius should be, same center should be it. Like this, concentric circles you do. So, as the current is moving upward, then it have the direction like this way. Hope you got it. So, that's the direction of magnetic field due to a straight conductor. In your NCERT textbook, there is an activity to show this also. On a plain cardboard, horizontally kept, you pass a conductor, straight conductor passing through it. Then you pass current through it. If you give some iron fillings, you can see when you pass current through it, these fillings will be in circular shape, they will be aligning. Concentric circles there will be. And to know the direction, you can use a magnetic compass. That question is there for 3 marks. Once it came, we'll do it. Hope you got the idea. Next question, let's see. Name the device used to magnetize a piece of magnetic material. Draw a label diagram to show the arrangement for the magnetization of the cylinder made of soft iron. Electromagnetic concept. So here, name the device used to magnetize a piece of magnetic material. You can use the name as solenoid. Because solenoid produce a stronger magnetic field in the interior region. So in that region, if you keep a material, it will be in the magnetic field for a long time. Then the material can be magnetized. Then that setup with an iron core is called electromagnet. So this figure, you can draw the pattern. See, it's a solenoid. It's connected to a battery. Current is passing through and switches there. Then if you keep this a cylindrical iron core, iron material, after few minutes, few time, this material will become magnetized. And it will be temporary magnet, because as long as current is there, it acts as a magnet. Then if you switch off it, for a few more time, this material shows a magnetism. Then we call as temporary magnet. We have two types of magnet, temporary and permanent. Permanent magnet, if we use it to produce, we make use of the other material like al-nico, aluminum, nickel, cobalt. Alloys we make use of for permanent magnet, because it can bear, it can keep the magnetic field for a long time than soft iron. For a temporary, we use soft iron, and for permanent, we use al-nico for this purpose. So for magnetizing, we can make use of solenoid. Hope you got it. Next question. So this figure is there. Please practice. This is the same figure, how to draw it. Okay? Hope you got it. Now, write the shape of the magnetic field produced by a current carrying straight conductor. State the rule to find the direction of this field. So, same concept, another way it is asked. So, write the shape of the magnetic field. So, write the shape of the magnetic field means they are concentric circles. So, they are concentric circles centered at the conductor. So it will be centered at the conductor, it is. So center will be the conductor, then concentric circles are there. So you have to write the shape only. Concentric circle is very important. You know, for a solenoid, the magnetic field inside the solenoid is parallel lines. That's very important. Parallel lines, because there is a uniform magnetic field. For a conductor, it is concentric circles. So that name of the shape is very important. Then, state the rule to find the direction of this field. See, very important, state the rule is asked. What is the rule, or which rule, name the rule is then. You have to name the only. But here, you have to give the name as well as statement of the rule should be given. So, to find the direction of magnetic field due to a straight conductor, we use the rule. Which rule? Right hand thumb rule. You know it. So, state the rule means you have to name it and give the statement. So, here it is right hand thumb rule. Now the statement, exact statement you have to give. You know the statement, what is it? Imagine we hold the conductor in our right hand such that thumb points in the direction of current. Then the curled fingers points or gives the direction of magnetic field around it. That's a minimum statement you should have. So please refer the NCERT textbook also to get the exact statement. Once more, thumb gives you what? Direction of current. So thumb should be along the direction of current. Then curled fingers, that gives you the direction of magnetic field. So fingers are in concentric circles only, hence this is concentric circles. So keyword I given, the statement should be as it is. Okay, imagine we hold a straight conductor in our right hand such that thumb points in the direction of current. Then the curled fingers gives the direction of magnetic field. Please refer the textbook also, make it sure, got it. Next question, let's see. Name and state the rule to determine the direction of A. So, name and state. Very important, you have to take care. Name should be given and statement also should be given. To determine the direction of a magnetic field produced around a current carrying straight conductor. Just we got it. Is it? Magnetic field produced around a straight current carrying conductor. We got it. It is right hand thumb rule. And the statement also we got. Previous slide. Then 2. Force experienced by a current carrying straight conductor placed in a magnetic field which is perpendicular to it. So, to determine the force experienced by a current carrying straight conductor, to find the direction of force, what we use, Fleming's left hand rule, we use it. So, it is, name of the rule is Fleming's left hand rule. The statement of the rule, exact statement you have to give. What is it? Stretch thumb, index finger or forefinger and middle finger of left hand in mutually perpendicular direction. The statement, if index finger shows the direction of magnetic field and middle finger shows the direction of current, then thumb gives the direction of force acting on the conductor. This is a statement. So there, the thumb will be showing, gives the force. This is happens when, if index finger, or you can use the word forefinger also, gives what? The field or magnetic field, and middle finger gives the current. So already in the 1 mark questions you made use of it. So statement is very important and the exact statement too. So if these two happens, then we get thumb was as a force. That is what Fleming's left hand rule. Thumb for force, index finger for the magnetic field, middle finger for current. FMC, FMC. Any code you can use it to keep in mind. So make sure the statement you're getting it. Next question. Draw a diagram to show the pattern of magnetic field lines on a horizontal sheet of paper due to a straight conductor passing through its center and carrying current vertically upwards. Mark on it the direction of current in the conductor and the corresponding magnetic field lines. State right hand thumb rule and check whether the directions marked by you are in accordance with the rule or not. See, it's a 3 mark question, came in 2024. It's 3 mark question. See, first part is an activity. It's given in your textbook. And say textbook it is given. So you take a cardboard. So magnetic field inside on a horizontal sheet of paper. A sheet of paper I take it. So a straight conductor is passing through its center. So if you take a straight conductor which is passing through its center. So through the center it's passing through. See, this way is passing. Then current carrying vertically upwards. So upward direction the current is passing through. Then what is the direction of the magnetic field cases? So here mark on it the direction of current in the conductor. Upward. This is current upward. Then corresponding magnetic field lines you have to do it. So corresponding magnetic field lines, if you use it, it will be concentric circles it will be. So circles you have to make it. And right hand thumb rule as after that. Thumb upward, curled fingers this way is passing through. So this is the direction of magnetic field there. So it's passing through this way. Okay, to get this one, by using the conductor, current and every arrangement, there is a figure in your textbook like this way. You might be seeing this figure. So practice this figure very well. On a sheet, you keep iron fillings is mentioned here. So instead of that, you can do this concentric circles. Here current is moving downward it is. So thumb is downward, then fingers are moving this way. So here see, the direction of current is like this way. I mean the magnetic field is this way. Current is a rheostat is there to increase and decrease the current. Ammeter is shown, a battery is shown, key is shown there. So this activity, if you practice well, you could draw this figure also. But here the current is downward in the question, current is upward is asking. Okay, so in the previous question, this question, state right hand thumb rule. So you have to give the statement also. Very important, right? The statement should be given, what we just mentioned previous way. Check whether the direction marked by you are in accordance with the rule or not. So you have to check whether it's right, means you have to say that it is in the concentric circle form and centered at this conductor. Hope you got it. It's a 3-mark question. Practice it well. The figure. Next question, let's check. Draw magnetic lines produced around a straight current carrying conductor passing through a cardboard. How will, so here is the same question in another way it is asked. In another region, the way. So first part is same. The magnetic how to do it. How will the strength, so here is the one subpart question. So it's again I gave. How will the strength of the magnetic field change when the point where magnetic field is to be determined is moved away from the conductor? So as the conductor is passing, suppose current is passing like this way, ISR. Then if one point here you imagine, one point here you imagine, what happens? As it moves further away, then magnetic field strength decreases. So nearby this one, it will be nearby, if you check it, these lines will be concentric and will be more closer. Then see, the width between them will be separated much, so that the magnetic field is decreasing. So as the further you move it, as the distance moved, then this way R or the distance increases, the strength of the magnetic field decreases. So that's the question, how will the strength of the magnetic field change? So it decreases, strength of the magnetic field decreases as you move further from the conductor. Okay, another 3-mark question. So that same figure you have to draw here, then make it sure. Next one other question, 3-mark question again. Draw the pattern of the magnetic field produced around a vertical current carrying straight conductor passing through a horizontal cardboard. Same, mark the direction of current and magnetic field lines. Done. Then one part is that name and state the rule which is used to determine the direction of the magnetic field associated with a current carrying conductor. So you are right, it is right hand thumb rule. Then statement you have to give. See, it's the same question, some addition or model changes are. Different region, the same question came. So how the pattern of the question? For that only, I kept this question here. Hope you are following. See, in the beginning I told you, in this chapter, 2 main rules. Right hand thumb rule, Fleming's left hand rule. Statement you should perfect. You should be perfect on the statement. Exact statement from NCERT textbook you refer and study it. Definitely you can score 2 or 3 marks from that one. Then how to apply it as a MCQs questions we done, pause the video lesson and practice it. It will help you for the exam, sure. Then diagram based questions. Here now, straight conductor we are doing many diagrams, we got it. Different way the questions came. Okay, next question let's check. State Fleming's left hand rule. See, the statement is asked again. Apply this rule to determine the direction of force experienced by a straight conductor carrying placed in straight conductor carrying current AB placed in a uniform magnetic field as shown. So here this AB is kept like this way and this conductor's current is passing upward. Magnetic field in that direction. So first statement of the Fleming's left hand rule. What is the statement? Exact statement should be given. Stretch thumb, index finger, middle finger of the left hand in mutually perpendicular direction. If index finger shows the direction of magnetic field and middle finger shows the direction of current, then thumb gives the direction of force or the motion of the conductor. This rule we use it. Here's the magnetic field in that direction, current upward, then thumb is inward. So we can say the conductor will move into the page The direction will be into the page you can use, or downward you can say. Move towards downward. Now, option B is there. So this is the part A. Apply the rule. Statement, you got it. Okay. Statement should be given. B. What will happen to an electron which enters in the same field in the same direction in which the current is flowing in the conductor AB? Give the reason to justify your answer. So, if an electron is entering in the same direction, okay, in which the current is flowing, then you know if electron is moving upward, current will be downward because current flows in the opposite direction of electron. So, magnetic field on the same direction, current downward, thumb is out of the paper, out of the page. So, direction is out of the page. Direction of electron, deflection will be out of the page. So, conductor was into, dash, it will be out of. Now, give reason to justify your answer. Of course, the direction of current is always in the opposite direction of electron. And when electron pass through it, it creates a current, hence a magnetic field is there. This magnetic field and the present magnetic field interact is there, hence electron experience a force. So, two justifications should be there. The movement of electron creates a magnetic field because it's a current. And direction of force is given by current in the downward direction, hence it's out of the page. So that 2 points you have to mention it. Okay. So movement of electron gives a current, hence a magnetic field. One reason. Then direction is opposite. Direction of current is opposite to electron direction. Hence, it's moving out of. So, two reasons you can get. That's a justification. 3-mark question. Please follow this question well. Let's take the next question. Define the term solenoid. What is a solenoid? That's a question. You have to define it. Draw the pattern of magnetic field lines around a current carrying solenoid. State how this magnetic field can be used to magnetize a piece of magnetic material like soft iron. So, like soft iron, just we got another question there, like electromagnetic, remember. So, define solenoid. What is solenoid? Solenoid is an insulated copper wire or a conducting wire wound in the form of a coil, cylindrical coil. Solenoid is an insulated conducting wire wound in the form of a cylindrical coil. When current passes through it, it produces uniform magnetic field inside it. Okay. Then you have to draw the pattern. Pattern of the solenoid figure, all of you remember in this chapter it's given. And say a textbook figure, you have to refer it. So it's given here, this is a solenoid. This coil wound in the form of a coil. Then if current is passed, this positive and negative of the battery, if you pass it, this will be south pole and this will be north pole. If you use Maxwell's square rule or right hand thumb rule reverse, if current passes, then thumb points is towards the north pole. Then just like a bar magnet, it gives the magnetic field lines. So this diagram you should draw there in detail about it. Okay. So please practice this figure also. Solenoid, one of the sure and most probable question from this chapter. Diagram, please practice it. Here one more part is there. State how this magnetic field can be used to magnetize a piece of magnetic material like soft iron. So if you keep the soft iron inside the core of the solenoid, there is uniform and strong magnetic field is there. So if you keep it inside it, the magnetic field lines pass through the material and it is get magnetized. That's called electromagnet. You got it? Okay, so that way you have to explain it. Regarding solenoid, many questions came in different regions. It's repeated. See, few more questions I will show you with some adds up by now. So this figure, please practice for solenoid. Next question, see, what is a solenoid? Draw a diagram to show the pattern of magnetic field around a current carrying solenoid. Fine. Name the region of the uniform magnetic field. See, this is a add up. Name the region of uniform magnetic field. So here in this figure, the uniform magnetic field is interior region. See, interior region of the solenoid. Parallel lines are there. So the magnetic field inside the solenoid or interior region of solenoid is uniform. So this magnetic field is the interior region or inside a solenoid. Interior region it is. See, one adds up there. Again, 3 mark question. For the figure, you will get the mark. What is the case? So what is a solenoid? It is a insulated copper wire or a conducting wire wound in the form of a cylindrical coil. It produces magnetic field when current passes through it. That is solenoid. See, another question. What is a solenoid? When does a solenoid behave as a magnet? When does means when current passes through it, it behaves as a magnet. So another adds up. Then draw the pattern of the magnetic field produced inside it, showing the directions of the magnetic field lines. So magnetic field lines, you have to show it. Again, the same pattern you have to draw. That's fine. Another set. What is a solenoid? How does current carrying solenoid behave when suspended freely and why? See, that's another add up. Give its one main use. So when it is freely suspended, if current is passed through it, it acts as a bar magnet. We studied it. So it aligns along north to south direction. Because a freely bar magnet can be used to detect the direction of the place. Always it will be along north-south direction. Solenoid also will act as the same. It will be aligned along north-south direction. You got it? Then give its one main use. It is used as electromagnet or a temporary magnet. In a soft iron core, if you kept inside, whenever current is there, it will act as a magnet. It can produce strong magnetic field than that of a bar magnet. So nowadays, whatever the electronic devices or appliances require or works with a magnetic field, we use electromagnets in that one. Next question, let's see. How is a solenoid prepared? See, the same question in a different flavor it came, is it? Differentiate between a circular coil and a solenoid. See, another add up. Between circular coil and a solenoid. Circular coil have one turn and they have a uniform magnetic field inside it. Then solenoid have a cylindrical coil. It have many number of turns. So each turn conducts same current and magnetic field. It's add up. So stronger magnetic field is produced by solenoid. Hope you got it. Draw the pattern of the magnetic field lines inside a current carrying solenoid. What does this pattern indicates? See, another matter. What does this pattern indicates? It indicates a uniform magnetic field. It's a parallel lines in the region. So it gives a strong and uniform magnetic field throughout the interior points. No change, no increase, no decrease. Same will be throughout the inside part. Next question, see. Draw the pattern of magnetic field lines of a current carrying solenoid. See, we done same. Then a bar magnet. Bar magnet figure is very important. You have to know it. In the NCERT textbook, it's given. See, this is the diagram for the bar magnet. North pole is there, south pole is there. Outside the bar magnet, north to south is the magnetic field direction. North, south. Then interior part actually it is south to north is going on. So start from north, end at south. So this way the field lines should be. And most important thing, never two lines intersect each other. So here see, here is more crowded, but still they are not intersecting. Take utmost care. This part is crowded there, but it's not intersecting there. That's very important. Okay, so near the poles, the magnetic field will be more stronger. You move far from the poles, then it getting separated more. So separated more means less number of field per unit place. There magnetic field is weaker. So bar magnet case should practice it. Then list two distinguishing features between these two fields. So solenoid produce uniform magnetic field only in the interior region. Okay, exterior the magnetic field is very weak or separated, we can say. But bar magnet gives strong magnetic field at the near the poles. That's a distinguishing factor. And look like same pattern is that both have. As you move further from the bar magnet, the magnetic field lines decreases. So weaker magnetic field is there. Okay, so that uniform magnetic field only for the solenoid inside it, and it will be constant throughout the points. Okay. Next one. So bar magnet figure you should practice. What happens when a bundle of wires of soft iron is placed inside the coil of a solenoid carrying a steady current? Name the device obtained. Why it is called so? So same concept in another flavor. It is called electromagnet. Electromagnet it is. Why it is called so? It is called because it acts as a magnet when electricity is there. It acts as a magnet when electricity is passing through it. So it's a temporary magnet also we can call. Okay, so electromagnet is, it produces magnetic field because of the electricity passing through it. Second part, draw the magnetic field lines inside a current carrying solenoid. What does this pattern of magnetic field lines indicate? So of course, the same thing. So it shows that there will be a uniform magnetic field and stronger magnetic field inside the solenoid. Same pattern again. So same concept, different way the question came. So you have to add up according to the topics. 3-mark question into the solar. In 2024, 3-mark question came from this chapter, most of them. Okay, then assertion, reason, like other questions too. Next question, let's see. A student fixes a sheet of white paper on a drawing board. He places a bar magnet in the center of it. He sprinkles some iron fillings uniformly around the bar magnet. Then he taps the drawing board gently and observes that the iron fillings arrange themselves in a particular pattern. So, particular pattern, the iron fillings are arranged. It's a practical oriented question regarding the magnetic field of a bar magnet. The same previous figure, you know, that's concept. For subpart questions are there. Why do iron fillings arrange in a particular pattern? Why do it arrange in a particular pattern? You know, iron fillings are magnetic material, so they align only along the magnetic field lines. Is it? So there is the wherever magnetic field is there, and the shape is given by the alignment of the magnetic, this iron fillings. B. What does the crowding of iron fillings at the end of the magnet indicates? So crowding of iron fillings shows there will be strong magnetic field. Strong field is there. C. What do the lines along which iron fillings align represent? The direction of the magnetic field lines, as well as you can say just magnetic field lines you can call it as. Shape of the field lines. So it will be curved like if you draw the tangent, you will get the direction of the magnetic field. D. If the student places a cardboard horizontally in a current carrying solenoid and repeats the above activity, in what pattern would the iron fillings arrange? State the conclusions drawn about the magnetic field based on the observed pattern of these lines. Very important, is a 4-mark question. So if it is done with a solenoid, horizontally is kept the paper, solenoid is kept in between, then iron fillings will be aligned in parallel lines will be. What does it shows? It gives a uniform magnetic field. Then state the conclusion drawn in the magnetic field based on the observed. So it will be uniform magnetic field throughout the interior part of the solenoid. Outside it gives just like a bar magnet. So as I told, just this solenoid act as a bar magnet. Interior will be straight, then outer will be just like that of a bar magnet. That figure we remember, same pattern you can draw as also support your answer. So what is the conclusion here? Solenoid gives the magnetic field just like a bar magnet. 4 mark question, 2024 it is. Please be thorough. Practice these questions again. You might have the theory studied well. So once you practice, you know the taste of the question, how to answer it. So each line, how to answer it. Next question, let's see. Earth wire is a safety. So it's regarding the domestic circuit. Earth wire is a safety measure in domestic electric circuits. Justify this statement, explaining its role in case of accidental leakage of electric appliances. So earth wire, in our domestic circuit, earth wire is one of the major safety measure. The appliances with metallic bodies, very important, the appliances with the metallic bodies are connected to the earth wire. So wherever you use 3-pin plug, the third pin will be connected to the earth wire. Because due to any malfunctioning or misarrangement of the connection work or circuits inside the metallic body may come touch with the live wire. So the user or we will get electric shock. To protect us from electric shock, the earth wire is connected. So that earth wire is taken to a conductor, good conductor of low resistance and buried under the earth. Our earth is a good absorption of charges, so current directly passes to the earth. There, the earth wire will be of low resistance device. Now, mainly copper, thick copper wires are used as earth wire to connect. So that copper wire will conduct the easy passage of the extra charges. Hence, it protects us from it. So, earth wire is a major safety device. Pause the video and get the clear-cut points. So, 3 points you have to make there. Earth wire is connected to metallic body of the device. Due to any extra leakage of current to the metallic body, the user may get electric shock. To protect that, earth wire take the current to the earth. This wire is connected to a conductor buried under the earth. Earth is good absorber of charge. So, it shows low resistance to the current, hence current completely go to this earth and the user get protected. That's the concept of this question. 2024, one of the region. Earth wire. Previously done fuse wire. You might remember, fuse wire is also another form of safety measure. It's of high resistivity but low melting point is there for fuse wire. When extra current passes through, it produces heat and it melts. Hence, the device will be safe. Fuse wire is there. Okay. So, instantly I just mentioned that's all. Earth wire, you keep in mind. Here's the next question. How does an electric fuse prevent the circuit and the appliances from possible damage due to short circuiting or overloading? So 2024 question, 3 mark. 2 more parts are there. How is the type of current used in household supply different from the one given by dry cells or storage batteries? Another 1 mark. For distant transmission of electric power, an alternating current is considered to be advantageous over direct current. Why? So 3 parts of the question is the first part, electric fuse. Just I explain now, electric fuse is a safety device which have high resistance and low melting point. So that's very important, fuse wire. High resistance should be, so it is of thin wires made up of, so resistance will be greater, area of course will be very less. Then low melting point. Important. Then how it is prevent the circuit? So how it prevent means it works on the heating effect of electricity. Heating effect of current it works with. That as the current passes through it, heat is produced. That is equal to proportional to resistance. It have a capacity, maximum capacity is there. That fuse rating will be there. So if more current passes, more heat produced and it melt. Hence it disconnect from the main circuit. That way the devices or the appliances will be in safe mode during overloading or short circuiting. Short circuit means live and neutral wire come to contact and more current pass through the circuit. So if fuse is active there, then fuse will melt at the time that other devices will be protected from higher current. It won't get damaged. Hope you got it? Next part. The second part. How is the type of current used in household supply, we use alternating current. AC, the alternating current. So it's more than a theory, it's a general knowledge too. In our household, we use alternating current. And it is different from the one given by dry cells or storage batteries. Batteries or dry cells give you the DC, direct current. First, the name difference. Now, what is difference is actually alternating current. If you draw a graph also, it will be better there. Alternating current, it changes the direction in each cycles. Continuously it changes the directions. So, if you plot a graph between the time and the voltage for AC voltage and time, if you take it, then the graph will be look like this way. That is for alternating current. It changes the direction. It's produced from AC generators. Now, direct current, if you draw the graph, the voltage variation if you do, then it will be just like a straight line. It gives always a straight current. Single direction current, no changes there. So, alternating current is used in household circuit. Dry cells gives you direct current, DC. AC, the name is alternating, changing, it varying the direction in each cycle. DC gives a straight conductor, straight current it is, no change in directions. Difference is there. So how is it different is given. Now one more question is there you can update more point about it. Alternating current is easy to transmit for long distance without any energy loss. Direct current cannot be transmitted long distances. Heat loss is greater in DC than AC. AC voltage we can increase or decrease by using transformers. DC cannot be changed. DC voltage cannot be changed by using transformers. So step up and step down transformers are there. As per that we can up or increase. Okay, these are the positive sides. In the third question you can apply that one. For distant transmission, electric power and alternating current is considered to be advantageous over direct current. Why it is? One more question. AC voltage can be increased to a load by using transformer. Hence, heat loss will be very least. Okay, DC cannot be changed the voltage, be constant. So, heat loss is very greater in DC. Hence, AC is more advantage for distant transmission. Hope you got it? 3 parts of the question, 3 marks. Next question, let's check it. A straight conductor is suspended horizontally with its axis perpendicular to the magnetic field of a strong horseshoe magnet. The conductor gets displaced towards right. Get displaced towards right when a steady current is passed through it. What will happen to the displacement of the conductor if these changes are done? What happened to the displacement is the question. It is the force on a conductor concept. In the NCERT textbook, you might have seen this figure in the circuit. What is it? A horseshoe magnet is there. In between, we keep a straight conductor, AB. It's an aluminum conductor, piece of aluminum. It is swing or it's hauled in a conducting wires like this way. On a stand it is kept. When you pass current through it, this aluminum rod, we can see this rod get deflected. In this question, first it is deflected towards right. Okay, then current pass through it. Then sub questions are there. Polarity of the horseshoe magnet is reversed. Polarity of the horseshoe magnet reversed means without changing direction of current, you change the direction of magnetic field. So Fleming's left hand only if you use it. Okay, in first case, horseshoe magnet current magnetic field is upward. If polarity is changed, then at the time the thumb is towards this way. Towards right, it is deflected. Now, if you just change the direction of, without changing the direction of current, if you change the direction of polarity of the magnetic field, see magnetic field downward, current is in the same direction only, then it will deflect towards left. So here in this case, it will be deflected to left. So change the direction of this one. Polarity of the host to magnet is reversed. Then left. Before it was right, so now it will be deflected towards left. Now direction of the current in the conductor is reversed. Same concept will be there. It's change the deflection. Without changing the magnetic field, only direction of current is done. 3. Current through the conductor is increased. So direction is not changed, but intensity increased. Then more force will be there or more stronger deflection. More stronger deflection will be there. Why more stronger deflection? Because force, the strength of the force increases. That force can be increased by increasing the current, increasing the magnetic field, increasing the length, and change the angle between, keeping it perpendicular to each other. Once more, the force on a conductor, current carrying conductor, kept in a magnetic field, you can change by methods like increasing the length of the conductor, increasing the current, intensity of current through the conductor, increasing the magnetic field, the external magnetic field increase it, and keeping it perpendicular to this direction of the magnetic field. So angle, magnetic field, current, length of the conductor, these are the factors happening. Second part of the question, name and state the rule for determining the direction of force on a current carrying conductor placed in a magnetic field. Same thing we've done already, Fleming's left hand rule. Name, then statement you give. Stretch thumb, index finger, middle finger of your left hand in mutually perpendicular direction. If forefinger or index finger shows the direction of magnetic field and middle finger shows the direction of current, then thumb gives the direction of force on the conductor. The statement you should practice and do it. See, read the question well, pause the video and get the idea clear, then go for the next question. See that the way the circuit diagram, see, here's the direction of force. If you reverse the direction of magnetic field, it will go that direction. Okay? If you reverse the direction of current, then also change the direction of this one. If you increase the current, then it moves stronger, it will be moving. So this regarding this activity, that question is there for the 4-mark question. See how important each diagram of this chapter. So please practice all the diagrams well. To draw the diagram, nowadays it's not possible, but it came in one of the previous year. Okay, so be sure about this diagram too. Another question. A straight cylindrical conductor is suspended with its axis perpendicular to the magnetic field of a horseshoe magnet. See the same question in another flavor it is. Let's check. The conductor gets displaced towards left. There it was towards right. When a current is passed through it, what will happen to this displacement of the conductor? What will happen to this displacement? When? If the current through it is increased, current increased, we done more stronger deflection. So force become more stronger. The horseshoe magnet is replaced by another stronger magnetic field. Again the same effect. So more stronger force, magnetic field increase, this force also increases. Direction of current through it is reversed. Then it changes towards, now it is deflected to left now, so it will be right. The direction of the deflection changes, towards right it will be. Then second, name and state the rule for determining the direction of force on current carrying conductor. The same thing, Fleming's left hand rule, you have to state it. See, the same question, another region is came, so the flavor changed. Be thorough with the theory, then you could answer it. For a current in a long straight solenoid, N and S poles are created at the two ends. North pole and south pole is created at the two ends. Among the following statement, the incorrect statement is. Incorrect statement, you have to get it. See, A, B, C, D, 4 options are given. One of the options is incorrect. Let's see, what is it? The magnetic field lines inside the solenoid are in the form of straight lines. Correct only. which indicates that the magnetic field is uniform at all points inside the solenoid. That is a correct statement. We have to find incorrect only. Is it? The strong magnetic field produced inside the solenoid can magnetize the soft iron placed inside it. We know it is electromagnetic. Is correct only. The pattern of the magnetic field associated with the current carrying solenoid is different from the pattern of the magnetic field around a bar magnet. No, we studied it is same. So it's not different. This is the wrong statement and that's a question. You have to find the incorrect statement. So C is the answer. Check D also. More accurate should be the answer. The N and S poles exchange positions when the direction of current through the solenoid is reversed. Of course, if direction of current is changed, you can change the direction of magnetic field also. That's the benefit of solenoid. You can change the direction of magnetic field. You can change the intensity of magnetic field. You can increase the intensity. That's all you can do. But the bar magnet, it is fixed. Okay. Next question, let's see. Consider a circular loop of thick copper wire lying horizontally on a table. Let the current pass through the loop anti-clockwise. So anti-clockwise, the current is passing through the loop. Draw the magnetic field lines to show the direction and the pattern of magnetic field inside and outside the loop. So there is a loop kept horizontal to this one. So if the loop is kept horizontal, see, one loop is kept horizontal to the table. And current is passing through anti-clockwise direction. So this is called clockwise, then this way current is passing through. Anti-clockwise is passing through. Then you have to show the direction of the magnetic field lines. See, one figure is there in your textbook, this one. You're familiar about this figure. One objective question already got it, similar question. Here it is kept vertically actually, then just to turn it, it will become the horizontal cases. Okay, so here, the same thing. So the current is passing through this way. So it is anti-clockwise if you do. Then current from the here, if you draw, it's the magnetic field will be right hand thumb rule here is here. So it's going from in to out. So south to north. That figure you have to make it. So practice that figure too. Okay. Then last part is there. Draw the magnetic. Okay. Then and outside the loop. Outside the loop, how will be it? So it will be going just like this way. It's passing through. Hope I got it. Next question, let's see. So this figure, you make it, just make it as horizontal. Answer will be correct. State the rule to determine the direction of, see another set of question paper. You have to state the rules. So you have to name it and give the statement. What do we give? Magnetic field produced around a straight conductor carrying current. You know it? Straight conductor carrying, it is right hand thumb rule. Right hand thumb rule it is. Right hand thumb rule. Statement you have to give exactly. Imagine we hold a straight conductor in our right hand such that thumb points along the direction of current. Then the curled fingers gives the direction of magnetic field. Then force experienced by a current carrying straight conductor placed in a magnetic field which is perpendicular to it. So regarding that also we done already. So it's a repeating question. It is Fleming's left hand rule. Fleming's left hand rule it is. Statement should be given. Stretch thumb, index finger, middle finger of left hand in mutually perpendicular direction. If index finger shows the direction of magnetic field, middle finger shows the direction of current, then thumb gives the direction of force acting on the conductor. So statement only, the same question repeating, another way it is asking. 2023 question. Another one question. State the rule used to find the force acting on a current carrying conductor placed in a magnetic field. See, the same question again repeating, but another flavor. See here what two parts are there. Given below are three diagrams showing entry of an electron in a magnetic field Identify the case in which the force is maximum and minimum respectively. Give reason for your answers. So it's a 3-mark questions. Very well you have to answer it. First 2 mark getting. So here reason also you would give and which is maximum. We studied that whenever charged particle pass through the a magnetic field, it experiences a force. Because movement of charge creates magnetic field and external one magnetic field is there, so they interact each other, there will be a force. That's given from Fleming's left hand rule. It is maximum when charges pass perpendicular to the field. So here out of these 3 figures, where is perpendicular? 1 is a figure, so it is maximum. Why it is? Because the current or the magnetic field produced by the electron will be perpendicular to the external electric field. Maximum force will be there. Okay? It should pass through it. Velocity should be perpendicular to the magnetic field. Next, minimum is asking. Minimum will be when this electron moves parallel or anti-parallel to the magnetic field. If they move parallel, there is no force. It will move on the same straight. So this is the minimum. Reason is, if move perpendicular, so V perpendicular to B, the speed or velocity perpendicular to B, then F is maximum. If V parallel to the magnetic field or anti-parallel, F is 0. There is no force. You got it? Fleming's left hand rule is used. See, 2023, one set of paper. Next question, let's see. Explain the meaning of overloading of an electric circuit. List 2 possible causes due to which overloading may occur in household circuits. Write 1 preventive measure that should be taken to avoid overloading of domestic circuits. So regarding domestic circuits, overloading and short circuiting, these 2 are 2 damage phases or causes create problems. So overloading is actually the current passing of excess current through a appliance or through a conducting wires. So in a connection, if excess current pass through it than the allowed limit, that is called overloading. So overloading means passage of excess current. Suppose a device have a rating of 5 ampere. If current passes 15 ampere or 10 ampere, that is overloading. Okay? Now, list 2 possible causes. So, 2 possible causes is, 1 is short circuiting. We can say 1. Connecting more devices in one plug. Connecting more devices to single plug points. Like in a single plug point, sometime 5 ampere range will be there. If you connect 3 or 4 together, then more current have to pass through it. It causes overloading. Then wrong connections. Wrong electrical connections. Like you connect 15 ampere line to a device with need 5 ampere. Of course, overloading will be there. It will damage the circuit. Got it? Now, one more part is there. Write 1 preventive measure. So, 1 is of course electric fuse you have to connect. Electric fuse always should be connected in series with the devices. The actual rating should be connected. Then, avoid connecting more devices to a single plug point. Then, proper electrical connections. These are the preventive measures you can mention. Hope you got it. Pause the video lesson and get the answer clearly. Next question is, list 2 factors on which the magnitude of magnetic field produced by a current carrying straight conductor depends. So another way of asking the question. 2 factors you have to make it. So of course, for the 2 factors, you can make it 1, intensity of conductor. Intensity of current. On that basis, the magnitude of the magnetic field will increase. You got it? Then the distance from the conductor. These are the two factors you can say. Okay? Then state the rule, second part, which determines the direction of magnetic field in the above case. So, statement you have to give right hand thumb rule. That statement completely you have to give it. Okay? Right hand thumb rule. Its statement you should give. Then draw the pattern of magnetic field lines produced in this case. So, already we done. Draw a pattern means you have to make the direction as first of all a conductor you have to show. Then the direction of magnetic field will be always concentric circles. If current is upward, then direction of magnetic field will be this way. Near is closer, further you go, it's separated. We discussed already. So here the first part and second part you keep in mind. Another one question. For the current carrying solenoid as shown, draw the magnetic field lines and give reason to explain that out of the 3 points A, B and C, at which points the field strength is maximum and at which point it is minimum. Regarding solenoid, one more question here. One more question it is. First part, then 2 mark, like that the questions came. So, magnetic field lines already you know how to draw it. The field pattern was shown in the previous slides. Here, at A, B, C, where it is maximum and where the strength is minimum, you have to find. So, maximum will be, you know, at A. The interior region, we have uniform and stronger magnetic field. So, the lines will be parallel placed. Then exterior points B and C, if you consider, at B it will be minimum. So wide separated magnetic field lines are at B. C will be nearly between A and B. So A will be the maximum, B will be the minimum we can say. C also of course minimum, but C is near to the poles we can say, north and south poles. Hope you got it? Next question. So 2023 question it is. Why is an alternating current considered to be advantageous over direct current for the long distance transmission of electric power? We discussed in domestic circuit, AC, alternating current is used for long distance transmission because in AC the heat loss is minimum. Heat loss can be minimized. But in DC, heat loss is maximum. So transmission loss is minimized in AC. AC voltage can be increased by using transformers. So if voltage is increased, as the power is constant, the current decreases. That cannot be done with a transformer with DC. Okay? Then how is the type of current used in household supply different from the one given by battery devices? We have done already the same question. That's part. One is alternating, another is direct current. Alternating current means the direction, the polarity changes continuously. Direct current, the polarity remains same in this one. 3. How does an electric fuse prevent the electric circuit and the appliances from the possible change due to short circuiting or overloading? That also we discussed in the previous. So this question is one part is separate, hence this came. Okay. So my dears, these are the questions. You may feel the videos long, but pause the videos and practice well. The previous last 2 years question papers in different regions we collected together. So chapters should be thorough before you. 6 marks minimum you can expect the question from this chapter. Make it sure 6 mark is safe in your hands. Okay, theory you studied, rules, statement you studied, diagrams you studied, factors on which each depends you studied. Practice it well. This way the questions comes from the chapter. Wish you all the best. See you in another video. Thank you for watching.